Hi, so Veritasium just uploaded a video on the so-called 3x+1 problem. Here's a snippet from that video.
Of course, there is another option, and that is that we'll never know, that the problem is undecidable. In 1987, John Conway created a generalization of 3x+1. It was a mathematical machine that he called Fractran, and he was able to show this machine is Turing complete, which means it can do anything a modern computer can do. But it also means that it's subject to the halting problem, a chance that the machine never stops running and so doesn't give you an output. And this does not prove that 3x+1 is also subject to the halting problem, but it is possible that given what we know, we may never prove the Collatz conjecture true or false.
Okay, so I want to discuss what Veritasium said about being subject to the halting problem, which does not imply that the problem is undecidable. So what do all these terms mean so that we have a consistent definition here? So undecidable for most practical purposes means that there is no algorithm for that particular problem. Okay, so there's just no algorithm to solve this problem, whatever that means. Okay, so an algorithm, for those who don't know, means that there's some kind of input and there's some kind of output and there's some kind of process in between, and very importantly, that process takes finite time, whatever that process is. Okay, so there's a finite input of finite size, then there's some computational process that takes a finite amount of time for some definition of finite amount of time, and then some output is produced. Okay, so an algorithm then needs to correctly answer the question, whatever it is, for any possible input over whatever the space that we're working with is. So what is the 3x+1 problem? So let's describe that problem. So the input here, there's only one input, is going to be some number n, which is going to be an integer. So the thing is that there can actually be multiple ways of representing this, but this is the way that I'm going to represent it. And then the output here, let's say, is some kind of Boolean. And we know what the Boolean actually means, but I might as well just describe what it actually means. So this Boolean is going to be true if f, actually I'm going to say it this way, if the trajectory of n is reaches 1. So what does that mean? So the trajectory refers to the Collatz trajectory. So that's what the 3x+1 actually refers to. So the trajectory I'm going to define as a function f, which is going to be defined for some number x to be one of two possibilities, which is 3x+1 or x over 2, depending on whether the number x is odd. So the 3x+1 case is if x is odd, and then x over 2 if x is even. Okay, and the trajectory just refers to starting with the number n, applying f to it, the result over and over and over and over, and if it eventually reaches 1, then we will say yes, and then false otherwise. Okay, so the question that we want to answer is there any integer n for which the result is false? Okay, so then the question is, well, how is the problem actually represented here? So the thing is that we might be able to figure out whether a particular integer gives a true value or not. So the question is there some integer n for which there's a false value that it outputs? So one thing that you might try is, let's suppose, and actually I'm going to give this a name. So this is going to be an algorithm I'm going to call single of n. So we're going to suppose that the single function, the single problem, is decidable. meaning that there is some algorithm for it. Alg for single. So for any particular integer n, I can figure out whether its trajectory actually reaches 1. The problem is that I can figure out whether one integer reaches 1, but I don't know whether there exists some number n for which the trajectory never reaches 1, whether there's some kind of loop or whether it goes off to infinity or something. So this does not imply, or does not immediately imply, that 3x plus 1 is decidable. Okay? And you may think, okay, well then it's undecidable then, but we can't actually say that. So subject to the halting problem is a little wishy-washy. If there was a reduction from the halting problem, then that would imply that it's undecidable, but for this specific problem, there isn't such a reduction. The reference to Conway's work is an actual reduction from the halting problem, and that's why that generalized problem is undecidable, whereas this one may or may not be, as Veritasium says. But again, it really depends on the encoding. Let me give you an example. So of why the generalized problem can be undecidable, but the specific problem can be decidable. So he mentioned these things called Turing machines, which are these tapes with some cells in them and a tape head that looks at particular cells, and it moves left or right depending on what the cells are and some finite state control that's controlling this whole thing. And one of the questions, centralized questions, is, I'll call it halt. So given some Turing machine M on input, let's say W, does M halt or stop on W? So there are special states that if you enter them will have the machine automatically stop. And so what we want to know is, when we start this machine up on this input W, do we ever hit one of those halt states? And this problem, and I've done it on the channel many times, is undecidable. That one actually is undecidable, okay, provably. But let's consider a variant. So this is something called a linear bounded automaton. So what is a linear bounded automaton? So it's the exact same thing as a Turing machine. So we have some tape and some cells, and we have, again, the tape head there. But here we are going to have the tape be fixed in size. So the string W here is occupying, at least at the start, the cells of the tape. And we have two additional cells at the end, which I'm going to have special symbols there, although it's not important what they are, to denote the ends of the input. And the question here I'm going to call halt for LBAs is, given some LBA and a string W, does this LBA, I'm going to call M, halt on W? And this one is decidable because if we have, so let's say that the length of W is n. So because we can't allocate additional cells here, that means that there are a finite number of things that can appear in each cell. There are a finite number of configurations of this LBA in total. And so what we can do is simulate this LBA for that amount of time. And if it hasn't stopped at this point, it never will stop because it must have repeated the configuration at some point. Okay, so the generalized problem here I'm going to call halt is undecidable. But since an LBA already is a Turing machine that just happens to have special behavior, is decidable. So that, of course, does not mean that 3x plus 1 is undecidable or decidable or not. I'm claiming here that it's not undecidable, which means that it is decidable under certain definitions of what it means to represent this problem. Okay, so here, if we represent this problem in a different way, then it is decidable. But if we represent it in this particular way, it may or may not be decidable in a certain sense. So let me give you a proof, quote unquote. So this is a proof that the 3x+1 problem is decidable. And it's actually very, very short. So what I'm going to do is I'm going to define a language. So if you don't know what that is, that's a set of strings. And it's going to be one of two possibilities. So it's going to be 0 or 1. And it's going to be the 0 case, otherwise, the opposite condition of what the 1's going to be. And then the 1 condition is going to be if the 3x+1 conjecture is true. So if this conjecture is true, i.e. all of the trajectories eventually reach 1, then this language is going to be set to 1. Okay, so I'm representing this language as a set of strings, either 0 or 1, depending on whether the conjecture is true. Okay, so it's either the case that the conjecture is true or it isn't. It's not some weird combination of like true and false or whatever. It either is true or it is not true, because it's just a statement about integers. Okay, although the truth of that is actually much more complicated than I'm making it out here. There's a Reddit discussion I'm going to link in the video description about this, but the thing is, this conjecture is either true or it's not true. Okay, or maybe it exists outside of our set system, but the thing is, it's either true or false. We may not be able to prove that it's true or false, but it is true or false regardless of that. So in either case here, whether this language is 0 or 1, whichever one of the case it is, there is a decider for this language. Okay, so no matter what happens, L is decidable. Why is it decidable? Because there's one possible decider that says 0 on all inputs, just say 0, and on all inputs, just say 1. There's another decider that just says 1. So I have two possible deciders that could exist here for this. So the language of just 0, there's a decider for that. The language of just 1, there's a decider for that. And so wherever the case, whether the conjecture is true or not, one of those two deciders is correct. I do not know which one is the case, because otherwise I would hand in my solution and get millions of dollars in fans and all that. But the thing is, there is a decider for this language L right here. Not necessarily the problem, although the language corresponds one-to-one with whether the conjecture is true. So there is a decider for this language, no matter what, guaranteed. However, the problem lies in determining whether or not the language is actually 0 or not. So it's a little bit of a pedantic definition, but the thing is that this problem phrased in this way is decidable. And you can substitute anything that you want here, like whether the nth digit of, whether the string 0 to the n is in the pi representation or something, or whether we will ever find life on extraterrestrial planets. Whatever condition that you want here, that condition is decidable no matter what, if you can phrase it here. Okay, so if phrased in this way, this problem is decidable. However, if phrased in a different way, corresponding to a different language, it may or may not be decidable. So it remains to be seen whether or not this phrasing is undecidable. So if the single problem is decidable, the 3x+1 may or may not, because that is a statement about infinite sets of integers. if it's proven that let's just say that we make some progress on the problem, and we are able to show that the 3x plus 1 conjecture is true from some number up. So let's say like 10 to the 10 to the 10 to the 10 or whatever. So just some big number. From that point upward, the conjecture is true. And so the conjecture needs to be proven for the remaining numbers. Then it actually turns out to be decidable in that case. Because think about what happens. So actually I'll write it down. So let's assume this. So let's assume 3x plus 1 is true for all n at least some big constant here. So n0 is a big number, possibly. So I'm assuming that this is the case. I don't think this is the actual case, but let's just assume that this is the case. Then what I claim to be true is that 3x plus 1 is decidable. Why is that the case? Well, what we can do is let's run our single, or at least we don't even need to run the single algorithm even if it doesn't exist. We can actually just simulate the 3x plus 1 problem long enough. So let's solve the 3x plus 1 problem. Oh, that was awful handwriting. So let's solve 3x plus 1 on some number n. Then what we're going to do is have a while true loop. So I'm just going to write the usual algorithm for the 3x plus 1 problem. So if n is odd, we'll set n to be 3n plus 1. Otherwise, set n to be n over 2. Then what we can do is if it escapes this bound right here, so like in the 3n plus 1 case, if it goes way up past the n0 bound, assuming that this is true, then we don't need to check anymore, because assuming that this is true, once you hit past this point, then that means that the trajectory eventually reaches 1. So in here, what we can do, squeezed into there, so if n is bigger than n0 at that point after the update, then we can return true. Okay, or some terminating condition or whatever. Okay, and I guarantee that this runs in a finite amount of time, so I claim that this thing is an algorithm, so it does halt in a finite amount of time, because think about what happens. And in fact, I'm going to draw it out. So let's depict all integers like this. And let's say that the n0 guy is right there. So, and then let's say that the integer n that we're given is right there. Well, if we're given a number bigger than n0, then this is already true. But then let's suppose that we have some number n. Well, obviously, wherever this number is, it could go down and back up, down and back up, down and back up. But it can only do so a finite number of times. Okay? So it can only do so a finite number of times before it either repeats a number down here or it escapes the bound up here. So if it escapes the bound, according to this, then that means that the trajectory eventually reaches 1. So the only thing that we actually need to check is that it actually reaches 1. And if it reaches 1, then it obviously is true. But if it repeats a number, then it obviously is false. So let's modify our algorithm to take care of this. So what I'm going to do is I'm going to move all of this down. So here I'm going to say if n is bigger than n0, return true, because obviously that claim is true. Okay. So then, now what do we need to do? So this is handling a particular number n, obviously, but we'll be able to handle every possible number eventually. So if n is bigger than n0, then we can return true. Otherwise, we need to keep a track of all the integers we've ever seen. So I'm going to make a list called scene, just a list. I'm going to write in Python syntax. Then what I'm going to do is I'm going to scene plus equal n using Python syntax, although it's not super important. So then what I'm going to do is I'm going to check if this is already in there. You can use a set to make this a little faster, but so if the number n that we just created right here has already been seen before, so if n is in the scene list, then that means that there is a loop in the trajectory and we'll never reach 1, obviously. So I'm going to return false. So whichever is the case, well, here this takes a finite amount of time, obviously. Well, here I claim that we're going to return true or return false in a finite amount of time, because if we do, suppose that we can't, well, that means that we'd spend an infinite amount of time down here. Well, there are only a finite number of integers down here. So either we will escape the bound, at which point the assumption kicks in, or we repeat an integer that we've already seen, which we will eventually find here. And checking whether a number is in a finite list takes a finite amount of time. So the thing is that this is true for a specific n. So if it is true for at least a specific number, then I can check any number I claim. So then all that we need to do to check whether the whole conjecture is true, so to check the 3x+1 conjecture, what we need to do is to run all numbers from 1, actually I should start at least 5, because there actually is a loop, the 1, 2, 4 loop that, as Veritasium mentioned, 5 until n0. Because there's no point to check the numbers after that, assuming that there has been an advance in a big advance in mathematics. This is a big assumption, by the way. So whether this is going to ever be proven, I have no idea, but it is decidable if this is the case. So, which a lot of conjectures have fallen in this particular way, that above a big specific number, the conjecture is true and there's only a finite number of cases to check. The thing is that it may not be possible in a finite, in a reasonable amount of time. So it might be in principle possible to check, but it just might not be practical to actually check. Okay. So the important thing is that we get the definitions of what decidable and undecidable actually mean. Okay. So just to recap. So the problem is decidable if you phrase it in certain ways, and possibly undecidable if you phrase it in other ways. Because it really has to deal with whether you can represent an infinite set in a specific way, or you're dealing with a specific input, or whether you're talking about the whole conjecture as a whole, then it may or may not be decidable depending on the encoding of the problem. Okay. So undecidable means that there's no algorithm to solve the problem, and which means that it must halt in a finite amount of time if there's an algorithm for the thing. So if we make some assumptions, then we can make some predictions. So we may or may not be able to show that 3x+1 conjecture is decidable, even if we can verify a single number, because the routine way of just checking all numbers, we may never run into a false number, and so we could run for an infinite amount of time and never find the thing that we want to find, so even if the conjecture is true. So there are encodings that are based on the halting problem, but even if we are doing something that is halting, that is related to Turing machines, that does not imply that it's undecidable because of this. So Turing machines the halting problem is undecidable, but a simplified version of a Turing machine is decidable. And if we encode the problem in a specific way, then it provably is decidable. But it's just not really any use to us. So the question is, what kinds of things can we show that if we make some assumptions, then we can actually show that it really is decidable? And this is a reasonable claim to make, even if it is actually false, because of Terry Tao's work and other people's work to show that a lot of trajectories will actually reach 1. So if it actually is true for all numbers after a specific number, a lot of conjectures have fallen this way, then it actually is decidable. Okay, but if this is not true, then it still could be decidable or not. It's very, very fine-grained as to whether it's decidable or not, depending on the encoding of the problem. I've spoken long enough about this. Please watch the video. It is very, very good. It was just this minor nitpick that I needed to pick apart. So if you have any questions about algorithms or the 3x+1 problem or undecidable problems, please put them into the comments down below. I'm always watching for them. Go watch Veritasium's video. It is fantastic. I just needed to rant about this specific thing.